In these alligator-infested backwoods, the final piece in the puzzle of Einstein's universe is being put to the test. This place stands at the leading edge of the exploration of gravity. Joe Giami is the head man.
Gravity will probably and hopefully confuse us for a long time before we figure out what it really is. And scientists are happy when they're confused and hot on the trail of something fun.
This is the Laser Interferometer Gravitational Wave Observatory, or LIGO for short.
Any signal we see is going to be from something really, really interesting and cool. Data from those kinds of sources would be really valuable to learn things about gravity and the nature of gravity.
This machine was built as an observatory, a chance to witness violent galactic events beyond anything we've ever seen before. One of the things I hope to see is when you get two stars called neutron stars. Now, a neutron star is probably twice or three times as heavy as the sun, but compressed into a ball about 10 kilometers across, so the size of a city. And there are places where there can be two of those things orbiting around each other at about 100 or even 1,000 times a second. The incredibly dense neutron stars spin round each other, churning up the space-time. As they spiral in, going faster and faster, Einstein predicts this sort of violent cosmic event will create something called gravitational waves. But what exactly is a gravitational wave? It's not that easy to describe. If a wave came through this room, it'd, what did I say? Ripples, yeah. Space-time isn't just something that's, you know, up there amongst the stars. It's here, right? It's in front of me and it's inside me. So when I move, I disturb it. I send out ripples in it. It's just like if I jump into a swimming pool and start swimming, I'll send out ripples on the surface of the water. It's the same with space-time. In theory, these waves would cause space and time to stretch and shrink as they pass through the universe. These waves are physical distortions in our reality. You know, they really are stretching and contracting the space and the time that we're in. But trying to see these gravitational waves using the LIGO machine is proving very difficult.
Gravity waves cause lengths to change in one direction differently than the other direction. So if I were very stretchy and a gravitational wave were going through me, this is what would happen. I would get shorter one way and longer the other way.
The machine works by using a laser beam to measure the distance between two sets of mirrors suspended at the ends of the two 4-kilometer-long tubes.
So from up here you can see pretty much all the key components. You can see running off to the right there and also running down under our feet are tubes that carry the light to the end stations. So there's a mirror here and there's a mirror 4 kilometers over that way. And when the gravity wave comes through, the distance between those mirrors changes.
They're basically just fancy rulers.
That's right, that's right.
But even after 5 years in continuous operation, the team hasn't been able to observe any violent gravitational hotspots. This is because they still haven't detected Einstein's elusive gravitational waves.
This is one piece of nature we haven't really observed right yet, to see gravitational waves, whether they really affect things here the way we think they do. We don't know where the sources are that we're looking for, so we have to look farther and farther out until we catch one.